Good morning, good evening, or good afternoon, depending on where you are in the world. I'm Dr. Wendy Bohon, and I'd like to thank you for joining us for today's webinar about what the 2023 Türkiye earthquakes mean for California. But first, let me tell you a little bit about Temblor. Temblor is a seismic risk modeling company with a staff of 10 outstanding scientists, developers, writers, and editors. Temblor has received funding from the U.S. National Science Foundation and has been a member of Willis Towers Watson Research Network since 2018. Temblor's clients include reinsurance brokers, insurance-linked security companies, global primary insurers, and government agencies. Temblor Earth News is read by about 50,000 people every month, and its free app informs the worldwide public about their personal seismic risk. Today's speakers are Ross Stein and Volkan Sevilgen. Ross, Temblor's CEO, is also a lecturer in geophysics at Stanford University and a former USGS senior scientist. As a fellow of the American Geophysical Union and the Geological Society of America, Stein received the Gilbert White Natural Hazards Award from AGU, gave a TEDx talk defeating earthquakes, and has received the Eugene Shoemaker Distinguished Achievement Award of the USGS. Volkan, Temblor's CTO, spent 7 years at the USGS with Ross before co-founding Temblor, and has published earthquake analyses in Nature and the Proceedings of the National Academy of Sciences. Volkan is past president of the Northern California chapter of the Earthquake Engineering Research Institute. Ross and Volkan will be presenting today's webinar. If you have any questions, please feel free to write those in the chat. We've set aside quite a bit of time at the end for Q&A and for community discussion. So take it away, Ross and Volkan.
Okay. Temblor is a California company with Turkish roots, so this topic has deep resonance for us. And what I want you to see here is that if we simply consider what earthquakes of this size would be like if, for example, they straddled Los Angeles or San Francisco, it's truly a bracing experience. And for a lot of good reasons, we focus the public on likely moderate consequence earthquakes, like a magnitude 7 on the Hayward Fault, or a magnitude 7.8 on the San Andreas, which by and large is far from population centers. Likewise, insurers tend to focus on events that have a likely return period of about 500 years or less because of regulatory pressures. This is a mistake. This earthquake, if it can happen in Turkey, it can happen in California, and we need to understand its consequences. So if nothing else, we can no longer ignore the possibility of very large double events occurring on both sides of Los Angeles or San Francisco. Now, why do I say if it happened in Turkey, it could happen in California? The reason is that the North Anatolian Fault system in Turkey and the San Andreas system in California are essentially sisters, faults with the same slip rate, length, straightness, and earthquake history. And in fact, both have given us magnitude 7.8 earthquakes historically, and each also has a creeping section that does not produce earthquakes in the center of the fault. And if we look at the behavior over the last 70 or so years of the North Anatolian Fault, we see the most spectacular falling domino sequence of earthquakes the world has ever known. However, even though we've been all waiting ominously for this remaining gap in the recent earthquake history in the Marmara Sea to rupture, this event did not happen there, but it happened instead on the East Anatolian Fault, where the two February 6 earthquakes struck. And this fault has a slip rate of about a third of the North Anatolian Fault. So the two faults that ruptured have slip rates of just 3 to 10 millimeters per year compared to about 25 millimeters per year on the major fault. So that's the first powerful lesson. These are secondary faults, if you like, wannabe faults, and yet they fired off these very large earthquakes. So let's ask the question, what are the California equivalents of the faults that ruptured in this earthquake? Well, as I've alluded to already, the North Anatolian and San Andreas faults are very similar. The fault changes its name in the Marmara Sea and calls itself the Marmara Fault, but it's the same system. Okay, what about the fault on which the magnitude 7.5 occurred, the second event in the sequence? Well, that occurred on the Shirgu-Kardak fault. And this is a very, very strange fault. And the reason is it's terribly misaligned to the tectonic forces that have to make it slip. If we put arrows showing you the sense of compression, you can see that the compression direction is almost perpendicular to the fault. In other words, this fault can't move unless it's as slippery as a watermelon seed, karpuzi if you're Turkish. And even weirder, this fault was formerly right lateral and recently has become left lateral. So this would be nobody's target fault for producing a major earthquake, and yet it has. But we have just as weird a fault in Southern California, the Garlock Fault, which is also perpendicular to the sense of compression, but also we know from paleoseismic work has produced large earthquakes. So we have a direct equivalent to the site that ruptured in the 7.5. Well, what about the fault that ruptured in the magnitude 7.8 earthquake? And that's the East Anatolian Fault. And in fact, in that case, we have many candidates. And so if we think about it, we have in Southern California, the San Jacinto or the Newport Inglewood Rose Canyon Fault. In Central California, offshore, we have the San Gregorio-Hosgri Fault. In inland or Eastern California, we have the Owens Valley White Mountains Fault, which produced a magnitude 7.6 historically. And in Northern California, we have the Hayward, Rogers Creek, and Macama Faults. So essentially, we have an embarrassment of riches of faults with slip rates, straightness, and lengths similar to the East Anatolian Fault. And the message of the Turkish earthquake is that any of these are capable of producing a magnitude 7.8. That's the clear statement. And that means that the stochastic event set being used by an insurer or the model being used by the public needs to have earthquakes of that size capable of occurring on those faults. Now let's take a look at Temblor's stochastic event set for Turkey. Now, our event set is not based on faults, but instead GPS strain rate and the past 117 years of earthquakes. So it doesn't include the large historic earthquakes or the means that are normally used, because we feel worldwide this is a much more consistent approach. And what you see here is that along the East Anatolian Fault trend, there are many earthquakes of magnitude 7.8 occurring in a 50,000 year period. Now, how do these earthquakes compare to the events that just struck? Well, you can see that the 7.5 occurred here and the 7.8 occurred here. My point is not that we have a disk where there's the two stars. Instead, my point is that we have about 30 magnitude 7.8s occurring somewhere along the East Anatolian Fault during the last 50,000 years. And if we compare it to the faults in the Turkish MTA catalog of faults, you can see that the distribution of these events is very consistent with a fault map. So the message here of about 30 magnitude 7.8 events in 50,000 years is about an 1,800-year repeat time for earthquakes of this size. So this is not a 1 in 500-year event, but nevertheless, it occurred and could occur on those similar faults in California. Now, how does this compare with the historical record? Well, interestingly, this record has been interpreted until very recently as producing no more than a magnitude 7.5 event. And yet, since the earthquake, this is the 1114 event, has been reinterpreted as being a 7.8. And this is the problem of the event set having too heavy a reliance on historical earthquakes. Even in Turkey, where the historical record is roughly 5 times longer than in California, we can be misled. We can expect or believe that no large earthquakes can occur based on that history. So this is an important message that the historical record, as valuable as it is still inadequate to give us the full sense of the possibility of large earthquakes occurring. So now let's compare our Turkish event set to the one we have in California. And what I want you to see over there in California is that we, in fact, have magnitude 7.8 events in the last 50,000 years on the Rogers Creek Hayward Fault, the San Jacinto Fault in the south, the Newport Inglewood, Garlock, Owens Valley, and Eastern California shear zone. And so this event set is consistent with this wake-up call that we've had in Turkey. And that's what we would like and expect to see. Now, beyond the question of, does California have faults capable of producing earthquakes this large, even if they're secondary faults? We've answered that question. But the next crucial question about this earthquake is that it's a double shock, is that we've had a 7.5 or maybe it's a 7.6 followed 9 hours and 100 kilometers away from a 7.8. Is that a concern for California as well? And my answer is yes. Here's why. When we look at the stress transferred by the magnitude 7.8 to the fault, to the Surgu-Kardak fault that would rupture 9 hours later, what we see is a large increase in Coulomb stress, the stress that tends to drive faults toward failure near the epicentral site of this earthquake. So this fault was fingered by the first earthquake. Doesn't mean that we have any insight as to when it could rupture or that it would necessarily rupture. What we say instead is that the first shock promoted the second. And once that second shock occurred, it transfers stress back to the rupture on which we just had, and we see a big decrease in stress along the central portion of the fault. And in fact, when we look at the aftershocks, aftershock rate suddenly drops in that portion of the fault after that second earthquake occurred. So if you like, these two earthquakes are interacting with each other and actually in some kind of a dance where they increase and decrease stress between them. Now let's take a closer look at this and look at the components of the Coulomb stress. That is the left lateral shear stress, which drives failure, and the unclamping of the fault, the forces that tend to keep the two faces in contact being released. And when we look at that, we can see that, in fact, it's the unclamping that's the big player here. In other words, there's about a 1 bar increase in shear stress, but a 3 bar unclamping on the fault. So if anything, it's the unclamping that seems to have played the largest role in the first earthquake triggering the second. Now you might ask, okay, is this a general observation that helps us understand and forecast earthquake interaction, or is this just a special case that happened to be here? Well, we just had a similar experience in California 5 years ago with the Ridgecrest earthquake, another double event, although smaller, a magnitude 6.4, which triggers 31 hours later, a magnitude 7.1. And just like the Turkish quakes, the first earthquake seems to, its most strong effect is to unclamp the fault that ruptured next near the epicentral site. So this is not a unique circumstance. And when we look a little farther, we can see that this occurred in the 1979 Superstition Hills earthquake and the Loma Prieta, so 2 other California earthquakes, as well as another double event in Japan. So that suggests that this earthquake interaction is important and gives us insights as to how one earthquake can trigger another, and reminds us that double events are not uncommon. And we always have to concern ourselves once an earthquake occurs with the possibility that that aftershock will be as large or larger than the first earthquake. Now that raises the question about whether or not this Turkish sequence is actually over, or is there more to come? And to answer that question, what we try to do is calculate now, not the stress interaction between the two ruptures, which you see here as black faults, but the stress transferred to the surrounding faults. And what we use are focal mechanisms. These are just the planes on which surrounding earthquakes have occurred, but we simplify them and we're looking at only the strike slip component of those focal mechanisms. And then what we do is smooth them into a grid of what we call receiver faults, faults which receive the stress from the two main ruptures, given the distribution of slip on those faults. And when we make that calculation, this is what we get. Okay, what do we see here? Well, we see these very large blue zones, which we call stress shadows, where the hazard or the stress has dropped. And then we see some concentrated zones of red. That's where the stress has increased and the hazard is increased. So here is the forecast for what could come next. Now, looking at this, you might say, okay, this is a calculation. How do we know that this calculation actually has fidelity to the Earth, that has some accuracy? And that's a very tough question to answer. But we can look at the background seismicity in the decade before the main shock and compare it to the aftershocks, because what we would expect is that the seismicity rate would decrease now in the stress shadows and increase in the stress trigger zones. Do we see that? So here it is. And now the background shocks, the shocks that preceded the main shocks, are magenta, and the aftershocks are black. And notice that the stress shadow zones tend to look magenta because we're seeing fewer aftershocks out here relative to the background shocks. Whereas in the red zone, so if I toggle this back, you can see that red zone is being filled by aftershocks. This red zone is partially being filled by aftershocks. And same with some of these other red zones. So there's a rough correspondence between aftershocks occurring in the red zones and background shocks being dominated because aftershocks are not occurring in the stress shadows. And I just want to point out there's also one peculiar spot here, and that's here where we have a big red lobe, but we're not seeing aftershocks. And that turns out to be the site of the 2020 magnitude 6.8 earthquake, which dropped the stress on the fault by 20 bars. And this red lobe has only increased it by a few bars, so it's actually still depressed. So I would argue that this rough correspondence between the model and seismicity lends some support to the forecast. Doesn't prove it's right, but that combined with past records of other earthquakes showing these relationships suggests that this can guide our sense for how hazard is changed. And given that, we basically see 4 areas where the hazard is now elevated to what it was before these 2 earthquakes occur. Those should be, in my judgment, the areas of concern. And now what I'd like to do is just say that this will fade. But when we have an earthquake in California, a large earthquake, whether or not it's a double event or not, we will also have these places where hazard is increased. Hazard simply doesn't drop because an earthquake has occurred. And now what I'd like to do is turn the talk over to Volkan to address the very important issues of shaking and damage that this earthquake has alerted us to with its unprecedented data set of observations.
Thank you, Ross. So the crucial part of this earthquake was the damage really created an extensive devastation in the cities. And I recognize California has much stronger buildings than in Turkey, but the observations that we had in this earthquake are pertinent to understand risks in California. And those are the high site amplification factors and extreme shaking near the fault rupture, and also the double hit two large earthquakes acting together to bring down buildings. So the damage was extensive, especially in downtown areas. And part of the damage is we've seen a lot of collapses, and perhaps we don't expect that many collapses in California. Nevertheless, they are providing a strong case for us to be able to understand how site amplification, which means the shaking amplifiers in soft sediments, correlated with shaking, with damages. So here's how the ground motion model observed in these very large network of strong motion devices in Turkey. And as you can see, the majority of the triangles close to the epicenter are in warmer colors, which is a higher acceleration values. And if you look at our model, what you would see at first hand, the model fits the observation well. If you look at the shaking versus distance plot, you would see a very large extreme shaking at close distance. These are distances up to 40 kilometers to the rupture. This is the first large earthquake that we ever measured with that many stations, these extreme shaking. So the model also matches those values. And again, distance, the shaking versus distance matches also very good. So one important thing about this is the model fits data in both high level of shaking and also a low level of shaking. So this is encouraging. Another factor of the shaking and how it's applied to building codes is when you have shaking in the y-axis and you have the shaking period, the oscillating waves, the shaking period on the x-axis, you have a code level for residential buildings. And this is essentially for apartments and houses. So this is the 10% in 50 years or 475-year return period, the maximum level of shaking. And you have a far more stringent code requirement for critical structures like hospitals and schools. And that is the shaking exceeding in 2% in 50 years or 2,475-year return. But the problem is the observed shaking exceeded even the critical structures level. So this means, especially for faults, especially for stations or locations close to the fault rupture, even if the buildings were built to the code in full compliance, they would still sustain damage beyond what code foresees. And that is something that, since we never had this close rupture observation before, is something that we need to also take into account when we are thinking about earthquakes in California. So this is the 10-story typical apartment building, and you are seeing the shaking exceeds far beyond the critical structure level. Another factor that this earthquake damaged the cities is through two earthquakes acting together. And essentially, the first quake finishes the job when the second earthquake finishes the job the first earthquake started. So here's in Kahramanmaraş and Malatya. They are shook by both of the events. The first event shook Kahramanmaraş harder than the Malatya case, but they both show similar level of damage. So that means if only the maximum shaking was important, we would see much extensive damage in Kahramanmaraş, but we don't. So that means the buildings were already damaged after the first event, and the second shock, large enough shock, essentially brought them down. And that is important for us to also think about how we are applying this information to doublets like the ones that Ross is mentioning. So another significant contributor to damage is site amplification. Site amplification correlates very well with damage. And we are in Kahramanmaraş region. Site amplification is the red to blue map, where high amplified sediments shown as redder colors, and the red dots are collapses. So what we are seeing is collapses or heavy damages fairly well correlated with high amplifying areas. This earthquake taught us another important thing, which is how site amplification changes with very short distance. So we are looking at essentially two sides of the road, where one side is very high amplifying, the other side is not. And what we are essentially seeing, the majority of the total collapses occurred where amplification is high. But both sides of the buildings may or may not be in same quality. Are there any examples that we can see same type of structures in both sides so we can see the impact of site amplification? And there is. And here's both sides of the road looks like the identical structure, and you are seeing far more extensive damage where the buildings are in high amplification zone. Here's another example in Türkoğlu, and what you are seeing is essentially, I would like you to see this road here, and both sides of the road behaves completely different. Eastern side is high amplifying and western side is not amplifying. And what you are essentially seeing, again, collapses are correlated with high amplifying zones. This distinction becomes even clearer when we superimpose the satellite-based damage map, and where the red blobs show the heavy damage and yellow shows moderate damage. And again, you are seeing that distinction fairly well. Well, although we don't expect to have collapses in California to be at this extent, but nevertheless, the site amplification correlation with damage is pertinent for California because we have a lot of areas that are in the same level of site amplification. So here's in Southern California, you are essentially seeing entire greater Los Angeles is in high amplifying zones, as well as Oxnard and other areas. And here's another example from Northern California, where urban centers and tech companies and all the populations essentially are in the high amplifying zones. And until this earthquake, we haven't really appreciated how impactful the soft sediments can be to damage expectations. And that should be part of our thinking while we are considering earthquake risk in California. Let me finish the presentation with this thought. Ross showed Turkey and California has similar seismic hazards. We have similar vulnerabilities in terms of high amplifying seismic risk, site amplification, and fault places close to rupture, creating extreme shaking, double earthquake acting together to bring down the buildings. Even though the buildings are better, those factors would still play a large role to determine what the ultimate cost of these earthquakes are. Thank you.
Thank you, Ross and Volkan. That was a very informative talk, and we have lots of questions already in the chat. So if you have additional questions, please feel free to put them in the chat, and we will we'll get to those right now. And if you have anything to add, we do really want this to be a discussion amongst the community, because we know a lot of you here have expertise both in Turkey and in California and in other places around the world. So feel free to raise your hand and we'll unmute you and you can go ahead and chime in. So I'll go ahead and get started with the questions. First, is there a rule to call an earthquake a doublet about time of occurrence after the main shock and its magnitude?
No, there really isn't. We use these terms doublet. We talk about compound earthquakes or progressive earthquakes. In a sense, most seismologists tell the public that the largest aftershock will be about 1 magnitude unit smaller than main shock. Except this doesn't always occur. Sometimes the aftershock is larger than the main shock or the same size. And then we give it a new name, so it kind of doesn't count in those statistics. What's important to recognize is that double events or equally large events are far more common than we allow ourselves to think.
Thank you. How would you describe the consequences of the Türkiye sequence for the extension of the fault system to the south into the Dead Sea Fault?
So you could see that in that slide where I give our forecast, there is a zone of increased hazard to the south, and that extends both at the northern extent of the Dead Sea Fault and the fault that tends to move in towards Cyprus into the Crete subduction zone. So both of those are in play, if you like, a higher rate of seismicity than before because of stress transfer. Whether or not that will trigger something on the Dead Sea Fault, we don't know. There's a small, what you could say is the probability of an earthquake on the northernmost Dead Sea Fault is today higher than it was before February.
Oof. All right. Dr. Ross, can we correlate the 1766 San Jacinto and Eastern San Andreas Fault doublet to the Kardak and East Anatolian Fault doublet?
It's a great possibility. I hadn't thought of it. And we should be looking at these things and try to understand if there are other doublets in the San Andreas history.
Was such a severe magnitude event in that region of Turkey forecast by the scientific community and most forecasting models? If not, why not?
Well, as you saw, the very best efforts, massive efforts to understand the magnitude of historical earthquakes tended to lowball what was possible. And that's not a criticism. If this earthquake has a repeat time of roughly 2,000 years, you can't expect a 1,000-year history to tell you everything you need to know. So in some sense, yes, this was forecast because the Turkish National Probabilistic Seismic Hazard Model had a very large hazard along the East Anatolian Fault Zone. Was it broad enough? Did it take into account large earthquakes on faults with measly 3 millimeters per year slip rate? Perhaps not. But my view is this is not a criticism of the existing probabilistic hazard model. Rather, this is an attempt to do a better job moving forward by understanding earthquake interaction and by recognizing that sleeper faults, wannabe faults, can actually fire off some very big quakes.
How does the Cajon Pass area, San Andreas, San Jacinto, Sierra Madre, Cucamonga fault zones compare to what happened with the East Anatolian Fault?
Well, that's interesting. So the Cajon Pass is an area where the San Andreas makes a bend, and earthquakes are extraordinarily deep there compared to any other area. It's considered to be a, quote, segment boundary by some geologists, but boundaries have a habit of being ignored by ruptures when they occur. So I would say, to the extent that the San Andreas has bends and breaks, as does the Surgu-Kardak Fault, they are similar. And I think the cautionary tale is, while we might expect those bends and breaks to stop some earthquakes, they won't stop them all.
Great. All right, Christopher, you have your hand up. Go ahead and unmute yourself and let us know your thoughts.
Yeah, this is Chris Mangus, and I think I have an interesting. I do a lot of geologic mapping in Southern California, particularly the Eastern California shear zone. And I've just completed. We're in the process of completing a study, which I think has a lot of relevance to this. I've studied the Pinto Mountain Fault, which is a big left lateral fault. It's just on the north edge of 29 Palms area, just on the north edge of the Eastern Transverse Ranges, the southern end of the Mojave. And I've also been working a lot with the right lateral. It's a left lateral fault, east-west trending, and it intersects across is actually the southern end of a lot of dextral faults, which are right lateral, coming out of the Mojave. And we've done a lot of paleoseismic work, and we have some pretty good. We've done about 29 luminescent states, that many of which are on this fault, in these fault zones, and we have some very good timing data, which suggests that both of these faults had a major earthquake within several hundred years of each other, about 1,500 years ago, and they were fairly large events. And I think this is I've published a little bit of this in some abstracts, but I haven't got it published formally. But we also have idea of the type of rupture. We mapped the surface rupture on this particular dated rupture zone, and we have evidence of a very complicated mapping of this rupture. But I think what this shows, and I think the size of the events, we have a rough estimate of between 2 to 4 meters. We don't know if that's a maximum minimum, but it's a good a general estimate for the surface rupture associated with this timed event. And so it looks like we're seeing two potential intersecting conjugate faults, actually, that ruptured within several hundred years ago, which I think is, again, I would also argue, I agree with you, are probably triggered, at least if not coeval, very close to a Ridgecrest, a paleo Ridgecrest event.
Thank you.
So much to learn, so much that we have not yet discovered. Thanks for bringing that up, because generations of work yet to be done, especially in these particular areas. So thanks for also bringing up triggering. Our next question is about the delay between the main shock and any triggered events. When considering the increased CFS for future earthquakes, could we expect particular timescale for the potential earthquake to be triggered? Is there any reason that delay time varies so much for triggered events?
It's a very, very tough question. Why is there 9 hours separating these two events, 31 hours separating the two Ridgecrest events, 30 years separating the 1966 North Anatolian fault and the 1999 event? As all we can say is that the behavior of this triggering is a lot like aftershocks themselves. You get a higher rate early, and then they get more and more spaced apart. We don't know why, in short order, why there are longer and shorter wait times, but it tells us that this phenomena can happen. And so that's why we can say with some confidence that this sequence isn't over, because 9 hours isn't long enough, 4 months isn't long enough. We could still have interactions that take place over years or even decades.
Yeah. Larry, I'll get to your hand in just one moment. I want to get to one more question real quick. In analogy to the areas of concern after the Türkiye sequence, what would be a corresponding area in California, given the local earthquake history, e.g. larger ruptures in the past?
Well, I gave you kind of a rogues gallery of East Anatolian fault-like faults that we have in Southern California, and I wouldn't be able to choose among them which is more likely. In Southern California, San Jacinto, San Gregorio, Newport Inglewood. Newport Inglewood is a particularly frightening fault because it tears right through the fabric of central LA. It was a fault that, since it looks like it's broken up into little pieces, people were initially kind of discounted it. Then we had the Kaikoura earthquake, a magnitude 7.6 on a bunch of little disconnected faults, and we realized, no, everything is in play. So I can't figure out which fault will be next or which fault is more likely, but all of these should be thought of as candidates for very large earthquakes.
All right, Larry, go ahead and unmute and tell us your thoughts, please.
Hey, good morning. Great talk from Cal OS Fire and Rescue and previously Ayala County Fire Department. I'm just, having been involved with the development of the shakeout exercise and the scenario, I was concerned for some time that we might have been underplaying the rate of injuries and fatalities because of the way the modeling was done. I mean, it's something around 2,000 fatalities, but what seems to be more of the case is that maybe our planning scenarios should be even worse than we had first gone with, just so that there can be an equal reaction in terms of preparing response capabilities and funding for that, the legislation that could accompany that, as well as the code issues. That's the one question I had is what's your sense of that at this point for the Bay Area and Southern California?
Well, thank you, Larry. And Larry, of course, has been heavily involved in emergency response for many years, and that's a crucial part of this picture. These are unknowables. Just ask ourselves what would happen if we had the Turkish earthquake sequence in straddling LA is a really frightening question, despite the fact that we recognize that fortunately buildings are better built in California and their residential buildings are built out of wood, all of which will make them fare better. Nevertheless, the consequences of an earthquake like that are breathtaking, and we've been shy, I think, about imagining them because we don't want the public to say, oh, you're claiming the sky is falling. You're trying to scare us with an Armageddon event. Well, no. Now we can say, no, we're trying to visualize an existing event that happened in another country that's a very close analog to California. We have a responsibility to think through what this would mean for us.
That's a great answer, Ross. And I think, honestly, I'm having a revelation that we probably need to socialize this aspect of it a little bit more and perhaps think about a shakeout version 2 and a haywired version 2 to take that potential into consideration.
Thank you, Larry.
So do you have an estimate for the insured loss from a similar earthquake occurring in California?
We've asked some of our clients if they would like to have us make that calculation, and they've said no. So, it clearly, if we compare the Turkish event and the California event, in all likelihood, the loss of life would be vastly lower in California, and the loss of dollars would be vastly higher because building values are higher. And because California is a litigious part of the world, and because Turkey, unlike California, has a mandatory earthquake insurance program. So something like half of the building losses were covered by insurance in Turkey. That would not be the case in California. It would be a very small component, and that creates conditions for all kinds of legal fights and whatnot. So, that's an armchair answer to a tough question, but that's the best I could come up with.
Okay, Volkan, this is specifically for you. How much damage was there in Turkey in places that did not experience ground motions exceeding the building code? Or to say in another way, how much damage can be attributed to lack of compliance with the code?
That's a very good question. We still need to work a little bit closely to understand how much the damage was, particularly for non-code compliance building practices versus how much of it is actually insufficient code requirement. And another complicating factor here is we still are trying to figure out how these two earthquakes are damaging and how those damages corresponding to these two earthquakes. So there's a little bit of a complicated case here, and we still need to work on that. There's no, short conclusive answer at this stage.
So Ken would like to know, is the 2019 Ridgecrest sequence over? Also, the Garlock sense of slip is opposite the San Andreas, where the Surgu Kardok and East Anatolian faults are both left lateral. Does that make much of a difference to your analogy?
I don't think so. First of all, the weird thing is that the Surgu Kardok fault was formerly right lateral, and it backed up and is now going the opposite direction. So you can see that it's been in a weird position from the get-go. So I would say that the similarities, that they're both weird faults that shouldn't move at all but do, just remind us that faults don't follow our rules, and that they have the ability to move even when, generally speaking, they shouldn't, and they should have retired already. And this is a problem. You know, it's a problem that you could have a magnitude 7.5 or 7.6 earthquake on a fault that's relatively short and has such a low slip rate of about 3 millimeters per year. Once you start looking at 3 millimeter per year slip rates in California, you have more faults than you can count. If they're long enough, then you can have these kind of earthquakes, and we never get the lengths right.
All right, quick question, and then Tony, we'll get to you. Does the fault intersection angle play a significant role in the unclamping effect?
Yes. So the geometry of faults influences the relative role of unclamping and shear. And, you know, Ken just mentioned the Ridgecrest earthquake, they're perpendicular faults. And in the previous question, we were talking about the relationship between North Anatolian and East Anatolian fault. Well, they have an angle of about like that, of about 30 degrees. So we see all kinds of geometries because faults tend to be much mangier and more complicated than we think. So in general, we like to draw lines, sinuous or straight lines. Faults do what they're going to do.
All these darn mangy faults out there. All right, Tony, go ahead and unmute yourself and tell us what you're thinking about.
All right, thanks for the excellent talks. Volkan, you showed the extent of damage to be different across the road in there, in Kahramanmaraş, I think. Could you give us a little bit of insight? Is it a geological boundary in terms of different rocks across the road? That's why you got that difference in the level of damage? And if so, what type of rocks that, or I mean sediments, may perhaps incompetent rocks under the high level damage versus the other part of the road? Thank you.
That's a very good question, Tony. And the model essentially understands it's not based on geology or geological map. It's based on how the rocks would be oriented or show up in the satellite imagery or satellite elevation models, and how we are associating that structures or shape into certain level of site amplification. So it's not geology based, it's more on the ground elevation and slope and parameters like that. And the changes are a lot more subtle than what we initially thought. So normally we would expect perhaps very sharp cliffs to be more bedrock-like. But what we are seeing in Turkey is even slight changes in these parameters can result in drastic changes in terms of site amplification.
Let me put it this way. If you're living in a place that's so flat that you would teach a child how to ride a bike, you're in trouble. If it just has a slope, just steep enough that you wouldn't teach your child to ride a bike, you're probably okay. So it's a very subtle difference in slope that corresponds to being in basin versus not being in a basin. And that seems to matter a lot.
All right, thank you.
All right, next question. Have you noticed or observed any correlations between specific building stories, I assume height, that experience damage and site amplification?
So looks like the shaking, especially for the close to rupture, really correlates well with standard building period for whatever Turkey has, about 10-story buildings. That would be 1 second period. So those, not only shaking level, but also what was the period of that shaking really matters. And taller buildings tend to have longer periods. So that seems like a more susceptible to heavier shaking because of that parameters. Also, another contributing factor, the building height is associated with the commercial interest of the builders too. So, if you have shorter apartment structures, they tend to be older, but it's maybe owner-built housing versus the taller apartments tends to be more commercially motivated structures where you really try to make it as cheap as possible and sell it to somebody else, and you are not really living there. So those commercial interest and scientific reasons how the shaking periods are correlated with that, they are both acting together to give us the consequences that we are facing.
Yeah, it's never simple.
It's not simple.
The second earthquake is so odd because it was massively misoriented to the regional stresses, as you report. Did the first earthquake reorient the stress field there, perhaps?
It influenced the stress field, but at 100 kilometers away, even given the size of the earthquake, it's a relatively small change. And so, when you're looking at these stress changes of, let's say, a bar or so. By the way, I can put a bar of stress across, Coulomb stress across my palms. If I just do this like that, and I orient my palms about 30 degrees to my arms, and I push as hard as I can, I just put a bar of stress across my palms. So it's incredible that stresses this small can play the role that they are.
Do you have any insights to share regarding directivity and basin effects?
Not at this point.
One thing we could say is that Malatya, remember, it's at the northeast end, just beyond the ends of both faults. That Malatya probably got directivity that Kahramanmaraş did not. So that's a possible explanation for why the damage was so great there. But we haven't looked at directivity strictly speaking.
It will show in the observation, and yeah, it is yet another. There are still a lot of research going on to fully understand how the rupture propagated. So once those studies mature, then we can look at the directivity a little bit more carefully.
Change gears with this question just a little bit. As ordinary California citizens, should we increase our preparations for how long we should prepare to survive much bigger earthquake disruptions? What are you doing to prepare yourselves?
Okay, great question. My wife and I just bought a house 2 years ago, and the first thing we did is spend a lot of money getting it seismically retrofit. We carry a ridiculous amount of water and means, food and things like that to take care of ourselves. We have emergency kits in our cars and in our house. So yeah, we should all, we live in this beautiful state. We take advantage of all of its wonderful elements, and most of that landscape has been built to us by the faults. So we got to be ready. And we have tended to think in terms of help being on the way immediately. And we saw that was not the case for so many Turkish people, despite a huge international response. So yes, the best thing we can do is to be ready for an extended period. And then we're in a position to help others.
Only one thing that I can add, keep your car, fuel onto the top, close to the top, not to the low level, or charge of the car. So you can actually get out of here if you can.
All these new things to think about that aren't necessarily included in the handbooks that were written 10, 15 years ago. Volkan, thanks for explaining the basin amplification effects. As you mentioned, most of the damage and collapses were on the east side of the major highway passing through the city, while the damage collapses on the west side of the highway was considerably lower. However, there was one seismic station on the west side, station 3125, and high PGAs over 1G were also reported from this station. Any other potential reasons for less damage and collapse on the west side? Maybe relatively newer buildings?
I need to take a look at that particular station. But I think one thing that I can see is sometimes when there's this high amplification occurs in the different frequency compared to rock. Rock tends to amplify or not attenuate high frequencies. So PGA is sometimes associated with high frequencies. And that could be one explanation. So maybe in some frequency band, you would see higher values, but they may not be pertinent for the structures there. That's one explanation. The second explanation would be, we do see some of the stations didn't quite worked as it should, especially in this second event. We are seeing two stations very close to epicenters. They show no shaking. So some of the stations are a little bit suspicious. So we need to be careful on how to fully interpret the results based on a single station.
We have a lot more questions, but we are closing out our time here. So I want to respect everyone's time and end on time, but we'll have one more question to close things out. What is the most surprising thing you've learned so far from the Turkey earthquake sequence as it relates to California and our future earthquakes?
Okay, so I'll give my answer. Volkan will give his answer. How about that? Massive earthquakes closely interacting on secondary faults. We haven't even discussed the fact that the 7.8 itself started on even a mangier, smaller secondary fault and ruptured like a freeway entrance onto the main fault itself. So to nucleate a magnitude 7.8, not even on the East Anatolian fault, but on what's called the gnarly fault, just a nothing fault, that's a shocker. And that indicates that, you know, any fault out there that we're looking at could be the nucleation site of something really big. That makes our life much more difficult.
And to me, the site amplification is somewhat included in hazard models for a very, very long time. But the amplification factors are minuscule compared to the extent of damage that we observed in Turkey. So we are seeing 4 or 5 times larger damage than what we would normally put in our hazard models. So that's a very interesting contribution that we didn't appreciate before. And another important factor is the extreme shaking. We tend to create artificial limit on what would be the largest shaking that this earthquake can create or any earthquake can create. And what we are seeing here is really exceeds that expectations. And lastly, Turkey has a very strong earthquake science community and structural engineer community. And the area is relatively a wealthy area, and the buildings are relatively well built. They are not, you know, the cheap housing that we were seeing in the other parts of the country in the earlier date earthquakes. So these are relatively new buildings, relatively well built, and seeing their damage that level, it was a surprise to me. I was expecting them to perform better, especially they're also identified as one of the high seismic hazard zone. So that was a little bit surprise for me to see the extent of damage.
Yeah. Thank you for those answers. And thank you to everyone for coming today. We appreciate you participating. We appreciate you being part of the community. All of us working together, that's how we're gonna learn more, keep each other safe, and keep the world more safe. So this recording will be available at the link that I just posted in the chat on the Temblor website on the webinars page. So that'll be up as soon as we can get it up there. Thank you again. Be sure to follow us on social media at Temblor across all platforms, Twitter, Facebook, LinkedIn. We will see you there, and we'll see you soon. Thank you, and have a great day.
Thank you, Andy. Thank you for the great questions.
Thank you.